The next LOS asks us to calculate and interpret measures of central tendency, including the population mean, sample mean, arithmetic mean, weighted average or mean, geometric mean, harmonic mean, median, and mode. Measures of central tendency identify the center or average of a data set. This central point can then be used to represent the typical or expected value in the data set. To compute the population mean, we simply sum the values of all observations in the population and divide by the total number of observations in the population. The population mean is unique in that for a given population there is only one mean value. The population mean is typically denoted with the Greek symbol mu, and again, the population mean is the sum of the values of all the observations in the population divided by the number of values in the population. The sample mean, denoted by x with a straight line over it, or x bar, is the sum of all values in a sample from a population divided by the number of observations in the sample. The sample mean is used to make inferences about the population mean. Note that when working with sample and population means, it is customary to use the small lowercase n to designate the sample size versus a capital or uppercase N to represent the size of a population. The population mean and sample mean are both examples of an arithmetic mean. An arithmetic mean is the sum of the values of the observations in a sample or population divided by the number of observations in the sample or population. The arithmetic mean or simple average has the following properties. All intervals and ratio data sets have an arithmetic mean. All data values are considered and included in the arithmetic mean computation. All data sets have only one arithmetic mean. The sum of the deviations of each observation in the data set from the mean is always 0, and the arithmetic mean is the only measure of central tendency for which the sum of the deviations from the mean is 0. When we refer to the sum of the deviations, we are referring to the sum of the differences between each observation in a sample or population and the mean of that sample or population. Sometimes it is necessary to compute a weighted mean. A weighted mean gives different observations a different influence on the mean. The weighted mean of a set of numbers is computed by summing the weighted value of each of the individual observations, where the sum of the weights is equal to 1. The easiest way to explain how to calculate a portfolio return as a weighted mean is through an example. Assume that we have a portfolio that is 50% stock, 40% bonds, and 10% cash. The weighted mean of this portfolio would then be 50% of the common stock return, plus 40% of the bond return, plus 10% of the cash return. Note how the sum of the individual weights, 50 plus 40 plus 10%, equals 100%. This example illustrates an extremely important investment concept. That is, the return for a portfolio is the weighted average of the returns of the individual assets in the portfolio. When calculating weighted average returns for a portfolio, the asset weights are represented by market weights, where the market weight of an individual asset is equal to the value of that asset divided by the value of the entire portfolio. The geometric mean is often used when calculating investment returns over multiple periods, or to measure compound growth rates. The formula for calculating the geometric mean return over n periods is the nth root of the product of 1 plus each of the n individual returns minus 1. For example, suppose that we have 3 annual returns, R1, R2, and R3. In this case, the geometric mean return is the cube root of the quantity 1 plus r times 1 plus r2 times 1 plus r3, all minus 1. Note that we use the cube root because we had 3 observations in our sample. A harmonic mean is used for certain computations, such as the average cost of shares purchased over time when equal dollar amounts are purchased periodically. In this application, the harmonic mean is calculated as the number of purchases divided by the sum of the reciprocals of the purchase prices. Consider an investor who purchases $1,000 of mutual fund shares each month for 3 months, where the per-share purchase prices are $2, $4, and $5. The harmonic mean is 3 divided by the sum of 1/2, 1/4, and 1/5. This is equivalent to dividing the total investment, $3,000, by the sum of 500, 250, and 200, which is the total number of shares acquired over the period. So, the harmonic mean gives us the average price per share for the 1,050 shares acquired in this fashion. Another measure of central tendency is the median. The median is the middle data point when a data set is arranged in either ascending or descending order. Half of the observations in a data set will lie above the median, and half will lie below the median. To determine the median, we simply arrange the data from highest to lowest value, or from lowest to highest value, and find the middle observations. The median is important because the arithmetic mean can be affected by extremely large or small values or outliers. When outliers are present, the median is a better measure of central tendency than the mean because it is not affected by extreme values. Since the median is the middle value, when a data set is arranged in either ascending or descending order, you may ask the logical question, well, what do I do when there is an even number of data points and there is no middle value? Well, in this case, you still determine the median by first arranging the data in either ascending or descending order, and then you take the two middle values and take the average of these values to determine the median. The mode is the value that occurs most frequently in a data set. A data set may have more than one mode, or even no mode. The next LOS asks us to calculate and interpret quartiles, quintiles, deciles, and percentiles. A quantile is the general term used for a value at or below which a stated proportion of the data in a distribution lies. Examples of quantiles include quartiles, where the distribution is divided into quarters, quintiles, where the distribution is divided into fifths, deciles, where the distribution is divided into tenths, and the commonly encountered percentile, where the distribution is divided into 100ths or percent. Note that any quantile may be expressed as a percentile. For example, the third quartile partitions the distribution at a value such that 3/4 or 75% of the observations fall below that value. Thus, the third quartile is equivalent to the 75th percentile. The formula for the position of the observation at a given percentile y with end data points sorted in ascending order is n plus 1 times y divided by 100. For example, assume that we have 10 observations. This means that the 75th percentile is partitioned at 10 plus 1 times 75 over 100, or 8.25. So when the data are arranged in ascending order, the third quartile is 1/4 of the way from the 8th data point to the 9th data point. The next LOS requires us to calculate and interpret 1. A range and a mean absolute deviation, and 2. The variance and standard deviation of a population and of a sample. The range is a relatively simple measure of variability, but when used with other measures, the range provides extremely useful information. The range is the distance between the largest and smallest value in the data set. The range is the maximum value minus the minimum value. For instance, if the maximum value in a data set would happen to be 30%, and the minimum value would happen to be 6%, then the range is 30 minus 6, or 24%. The mean absolute deviation, or MAD, is the average of the absolute value of the deviations of individual observations from the arithmetic mean. The computation of the MAD, or mean absolute deviation, uses the absolute values of each deviation from the mean, because the sum of the actual deviations from the mean will equal 0. To compute the mean absolute deviation, you simply find the difference of each observation and the mean, add these differences, and divide by the number of observations in the sample. Now, let's talk about the population variance. Variance is defined as the average of the squared deviations from the mean. The population variance is typically denoted with the Greek letter sigma squared. To calculate the population variance, we take the difference between every observation and the population mean, and we square each of these individual differences. We sum the squared differences and divide by the number of observations in the population. The sample variance is the measure of dispersion that applies when we are evaluating a sample from a population within observations. The sample variance is denoted with S squared. The sample variance is calculated using the same procedure that we used for calculating the population variance, except we divide the sum of the squared deviations from the sample mean by n-1, where n is the number of observations in the sample. The population standard deviation is simply the square root of the population variance. Likewise, the sample standard deviation is the square root of the sample variance.